apparently everybody's awake now that we're doing contact tracing stuff, so let's continue with that. Christoph, please take it away.
Great. Thank you for the introduction. So now this is going to be a bit more theoretical, and this is joined up with my advisor Kshishi. So we've heard about automated contact tracing. So now here the A is about automated and not asymmetric as beforehand. And so for contact tracing, it's a disease control matter, and we want to notify users about contacts with other infected individuals. And this should be automated. And we all know COVID, and this spawns like a lot of research in this area. And it culminated in Google and Apple jointly deploying a protocol based on DP3T, which you've just seen in the talk beforehand. And in general, these protocols use smartphones and Bluetooth Low Energy. So these devices interact, they have some sort of protocols, and at the end, there is a contact. So a contact is some shared state of the devices, allowing for the following functionality. Should the user A become sick, they report to the server. The user B regularly checks in with the server, and since they had a contact beforehand, the user B will be alerted. So this is the basic property that we want of these protocols. And now, what about the privacy? So just by this property, we can see that it creates digital evidence. So suppose we have a judge and they want to see whether A and B have met. They just confiscate their phones, which a judge might be able to do, report the user A, check B's phone, and then if B got an alert, they know that there was a contact, like they physically met. And now this is a privacy and a deniability issue, and this follows from the basic definition. And the issue is that this is a misuse of the protocol and the privacy concern for users. Now, since we cannot get this strong form of deniability, we're going to look at contact time deniability. So now it's going to be harder for the judge because they need to decide whether A and B actually met at the time T. And what we show in our work is that given this form of deniability is quite hard to achieve. Namely, there is some sort of dilemma between contact time deniability and replay security, and this holds for a large class of protocols which encompasses many practically relevant boxes. Let's now dive into this result in the remainder of this talk. So first of all, I want to tell you which protocols it applies to. So first of all, the protocols need to be unidirectional, so messages only flow from A to B. And for here, it's a single message, but it could be multiple ones. And essentially, the condition is now that if B receives the message, then this corrected condition holds. So one single message constitutes a contact. And then it should be decentralized. We've also heard about that in the previous talk. So now this central server is essentially a database. So users report as sick by uploading data, and other users download data and then can locally check on their device whether they should be alerted or not. And now these are the protocols we consider. And now for our contact time deniability game, we have an honest user A and a malicious user M, and they interact at some point in time. And the malicious user might deviate from the protocol, and their aim is to convince the judge that they actually met the user A. So this creates some sort of gossip or some provable edge in a social graph issue. And now a protocol is contact time deniable if deciding this for a judge is hard. So given this proof and the faults of the users, the judge has a hard time deciding whether they met at the claimed time T. And in our work, we actually don't have this binary property, but one that is parameterized by some sort of delta. And this delta quantifies how certain the judge can be. So if you look at this equation here, essentially delta is small, the judge is very certain when the contact happened. And if the delta is large, then the judge doesn't really know a lot. So essentially, what this means is delta contact time deniability is only meaningful if delta is large. Good. And then our security property is replay security. And security in these contact tracing protocols is concerned with malicious users not being able to create spurious or otherwise malicious contacts that didn't happen in reality. So as you might expect, in replay security, the user A first interacts with the user M. Then the user M has to wait for delta 5. So again, we have some parameterized version here. And then the user M interacts with the user B. And the user M wants to cause a contact between the two honest parties, even though they didn't meet in reality. And it's replay secure if this is not possible for the adversary. And now with this, we can, and what I want to mention is that delta replay security is only a meaningful property if we consider small delta. So ideally maybe sub-second, which essentially means the user N receives a message from the user A, and this message is immediately not really useful to replay to the other user B. And now equipped with this, let's look at our main theorem. And the theorem states that if a protocol is unidirectional and decentralized, so these properties I showed beforehand, and it is delta replay secure, then it can at most be delta prime contact time deniable, where delta is strictly greater than delta prime. So I said that this is a dilemma or an impossibility, and this is because if we recall from our previous slides, for replay security, we want a small delta. But for delta and delta prime, for contact time deniability should be large. Now looking at the inequality, we are now left with the choice of choosing either a meaningfully replay secure protocol that is not contact time deniable, or the other way around. And now the proof is actually quite easy to sketch and quite intuitive. So what we are going to show is, assume that the protocol is delta replay secure. We will show that it is not delta contact time deniable. So this is kind of the edge case of this inequality we had beforehand. And below here you see the contact time deniability game. So suppose that the user A sends a message and user M receives it at time t. Now the user M in the first step timestamps this message MA. So a timestamp is some publicly verifiable proof that the user M had possession of, or that they knew the message MA at time E. And how do you realize such a timestamping practice? Well, you just use a blockchain, for example. So I want to emphasize that the blockchain is not used in the protocols themselves. It's just the malicious party that somehow uses it. But you could think of any other timestamping service offered on the internet that is trusted. And now what the judge receives is the message and the calls of the users. And now in the first step, the judge kind of does some sort of thought experiment. So they consider what would have happened if they would have received the message MA at time t. Would it have led to a conflict with the user A? And essentially the judge creates some sort of dummy phone, but the technical details are a bit too intricate for the remainder of this tile. What I want to say is that here this unidirectionality and this decentralized property are important, that this is achievable or possible. Then now in the second step, the judge now notices that, well, the message is actually in the blockchain as signed key. And now what you can see here on this timeline is essentially this creates an upper bound on the time that the interaction could have happened. And now in the third step, what the judge does is they do know that the protocol is delta replay secure. And so now the core insight is that since in the first step the judge is certain that the message could have been received at time t, they know it could not have been too early on, at mostly at the steps in time. Because otherwise this would kind of constitute a replay attack. And we do know that replay attacks are not possible here. And now if you look at this timeline, you can see that this point t is quite tightly boxed in with at most delta steps in time on each direction. And so what this means is that the protocol is not delta contact time deniable. And that's exactly what we wanted to show. And this basically concludes the proof sketch. And now what is interesting is that if you look in the literature, and there's loads and loads of proposals for these contact tracing protocols, the gist of this table, so you don't have to parse it all right now, is basically that many sensible combinations that are allowed by our impossibility result do exist in the literature, and people did propose them or discuss them. And please refer to the paper for details on this table. And Now, so let me conclude. So what we've seen in this talk is that deniability is not achievable for these unidirectional and centralized protocols. And the reason why I say not achievable is because effectively replay security is a really basic and important security property for these contact tracing protocols. So we kind of don't want to give that up. So deniability is probably what we will kind of not do. And I want to mention in the paper, we extend this result to all decentralized protocols, but this requires assuming a stronger judge. This might not be that realistic, but yeah, you can judge for yourself, I guess, by reading the paper. And now, the final point is, I think many people here are more practically oriented. And now you might think like, why would I care about theoretical results? And I want to see some graph and some numbers and so on. And the reason is why we do this. We want to help you like identify which points are worthwhile to like consider and to implement. And also, as a final remark, the previous talk I think is a really nice and creative way to kind of break out of the model in some way that gives users more control and more active participation. And I think those avenues should also be explored. Thank you for your attention. I'm happy to take questions.
Thanks, Christoph, for the great talk. We have a question here up front, or maybe there, Paul. That's easier.
So I just want to make sure I understand. The whole thing is based on an assumption that basically you're identified. So basically, anonymous reporting is you just assume none of these protocols have that.
What do you mean exactly by anonymous reporting?
Well, if you just have, effectively you have a design in which, there's a report that a given individual or somebody who tested positive was, say, here at this time, and you just know that you were at some point exposed to somebody who tested positive, or sometimes I had a design where a group of people, and that's all you know. You just know a distinct group of people. Then presumably the impossibility results wouldn't apply in that case, or is that not true?
So I'll try to answer it, but maybe we can also talk offline because so essentially the result applies to all kinds of protocols that are like EP3T, like most of the things you've seen in literature. And yes, essentially those where you, for example, as we've seen before, upload some random like PRF outputs or so on. So this would also capture these protocols. Like would be captured by our impossibility result.
We have time for one more quick question, but please keep it short, both the question and the answer, so that we don't run out of time even worse than we are already doing.
Are you aware of any examples of replay attacks in contact tracing, or is there a clear incentive for a user to make that kind of attack?
So I think, for example, the literature, I'm not sure if there were actually attacks, but you could think of, for example, a voting day where then someone replays identifiers from a hospital where people get tested. And then, for example, certain voting groups might prefer to stay at home because they don't want to infect users. Other voting groups don't care. And this kind of sways the election. Would be an issue.
Okay, thanks everyone. Let's talk Christoph again.